Greetings, it's Paul Bamberg with the introductory video for Class 19 of Math 117 on continuous martingales. Before we think about continuous martingales, though, let me give you a nice example of a convergent discrete martingale. In the theory of random walks, this is known as a symmetric random walk with absorbing barriers, but in financial terms, we can imagine it as a fair game that you play in a casino. The roulette wheel has no zero. That makes it a fair wheel with half red numbers and half black numbers. And every round you bet one chip on red. You win a chip if a red number comes up. You lose a chip if a black number comes up. And you start out with capital K, with K chips, so that after n spins of the wheel, you have your K chips plus the sum of n random variables x sub I. X sub I is either +1 or -1, depending on whether you win or lose on spin I of the wheel. However, there's a catch. If your balance ever drops to 0, you have gone broke and you have to leave the casino. And being a prudent gambler, you also have made up your mind in advance that if your balance ever rises to capital M chips, you're going to declare victory and leave. That's a good idea, because if you keep playing forever, the probability that you will eventually go broke is 1. Now, we want the sample space to consist of infinite sequences of spins of the roulette wheel. This creates a bit of a problem because you might leave the casino, and we will remedy it by saying you've instructed the croupier that if you're not around, he is to place a bet of 0 chips on your behalf. So that means that x sub I is plus or minus 1 as long as you stay in the casino, but it drops to 0 after you've left. In either case, it's a fair game. The nice thing about this martingale is that it's clearly convergent. It converges to a random variable that almost surely either has the value 3 or the value 0. Let's think further about this limit. We could use as our sigma field the sequence of numbers that appear on the first n spins of the wheel, but as is often the case, it's simpler to let it be the sigma field generated by our random number. We just pay attention to what sequence of red and black has occurred. So after n spins, an element of our sigma field consists just of a sequence of red and black. Now, I said almost surely you will leave the casino, but it's only almost surely. You could, in principle, keep betting forever. You start with 2 chips, the wheel produces a black number, you're down to 1 chip, then a red number, you're back up to 2, and if the sequence black, red, black, red, black, red persists forever, you will never leave the casino. However, that's an event with probability 0. So I'm still correct in saying that almost surely you will leave the casino as a winner or loser. And the limit of this martingale is a random variable. We can name it y sub infinity, and y sub infinity for any sequence of spins omega almost surely has the value 0 or m. This is true even if you make m very large, because the random variables y sub n are all less than or equal to m, and so based on the little bit you know about martingale convergence, this martingale, being bounded, will almost surely converge. Now, of course, what interests you in this case is the probability that you will leave a winner rather than a loser, and that question is trivial to answer. The answer is k over m. Why? Because y sub n is a martingale. A necessary requirement for a martingale is that each y sub n in the martingale has to have the same expectation. When you start out, you've got k chips, so y sub 0 has expectation k. The same is true for each y sub n, and it's true in the limit. So the expected value of the limit y sub infinity has to equal k. The only way that can happen is probability k over m of having m chips, probability 1 minus k over m of having 0 chips. Now let's try to think about a continuous martingale. We're going to have a filtration that is indexed by the positive real numbers instead of by the positive integers, and random variables adapted to this filtration. That is, random variable x sub t will depend on what has happened up till time t. The requirement for a martingale is still the same. If we think of a time s that's earlier than time t, the expected value of x sub t conditioned on what has happened up till time s has to equal the random variable x sub s. In fact, we've been thinking about this principle in conjunction with stock prices. Suppose that x sub t specifies the fair price of a stock as a function of time, then this martingale property says that if at time s you buy a share for its fair price, the expected value at a later time t is equal to what you paid for it. That's what made the price fair. Now you can think of this time evolution as sort of a continuous limit of a random walk. You have a lot of independent small steps, each having expectation 0. And on the basis of the central limit theorem, we can say that the sum of all these changes will have a normal distribution, also with expectation 0, but with a variance that keeps getting larger and larger, a variance that's proportional to the length of time that has elapsed. Here's a concrete example of such a continuous martingale. Imagine an electronic casino. You play at this electronic casino on your computer, and every millisecond what the computer does is add or subtract a tiny amount. So you start out with a balance that's k, and every millisecond this either goes up a little bit or down a little bit. The computer will have a random number generator which has some seed. So in this case you can think of omega as being specified by the seed for the random number generator. That seed will determine the entire sequence of pseudo-random numbers. Your balance will be a function of time. It will be a random variable that gives the price at that time, dependent on the sequence of random numbers as determined by the random number generator. And since the probability for adding and subtracting a small amount is equal, this sequence is going to be a martingale. We have a filtration again. At every time we have a sequence of increases and decreases resulting from what happened at all times s that are less than t. And for any particular sequence of random numbers, the sequence of random variables x sub t is a continuous function of t. Actually, it's continuous only in the limit where the price changes take place at arbitrarily short time intervals. If we have the price changes taking place only every millisecond, the function is not quite continuous because the domain consists just of times that are an integral number of milliseconds. Now, let's imagine that your balance starts at 2, and as before, you decide you'll exit the program either if your balance goes down to 0, you're a loser, or your balance goes up to 3, you're a winner. That makes this martingale be bounded, and therefore there's a random variable x sub infinity, The value of this will depend on the sequence of random numbers, because the sequence of random numbers will determine whether you're a winner or a loser, but the value of x infinity is almost surely 0 or 3. The event that you never get to 0 or 3 is not impossible, but it has probability 0. So, the random variable x sub t for any sequence of random numbers is based on following the paths until they either lead to 0 or to 3, taking 3 times the fraction of the paths that go to 3, plus 0 times the fraction of the paths that go to 0. And now we can check that we've got a martingale. We look at the expectation of x sub t conditioned on the sigma field f sub s at an earlier time. Since x sub t is the conditional expectation of x infinity conditioned on f sub t, and since f sub t, which involves what happens up to time t, is a finer partition than f sub s, we can apply the Tower law. Say we can just condition on f sub s. The intermediate conditioning on f sub t accomplishes nothing, and that is x sub s. What have we shown? We've shown that the expectation of x sub t conditioned on f sub s is equal to x sub s. That's precisely the condition for a martingale. And furthermore, we know that we've got a limit, x infinity, so x sub t is a convergent martingale. You can make a discrete martingale out of this by just sampling the price every second. Now, there are lots of results we're going to have to prove starting today and continuing into the next couple of classes. The first one, which I've numbered step 0, is mine. I'm going to prove as a sample problem that if we have a normally distributed random variable with expectation 0 and variance sigma squared, the expectation of the exponential of that random variable is e to the 1/2 sigma squared. This is a rather messy result to prove, but we'll need it over and over again. The next steps are yours. You're going to show that 3 things are martingales. The first one is going to be WT. We're going to assume that it is given by the central limit theorem, has expectation 0 and variance t. And we're furthermore going to assume that WT minus WS is normally distributed with a variance equal to the time difference, t minus s. And finally, we're going to assume that what happens between time s and time t doesn't depend on what happened at an earlier time. People who believe in technical stock analysis believe that by looking at how the price has been evolving recently, you can make predictions about what's going to happen in the future. This assumption says that that's impossible to do. And under these assumptions, we'll show that W sub t is a martingale. In fact, I probably shouldn't have said that W sub t is the share price. It's just a random process, a random walk that determines the share price. Then we're going to show that W sub t squared minus t is also a martingale. We did the discrete version of that result the last time. Next, you're going to show that if you take the exponential of mu t plus sigma times this WT, this can only be a martingale if the value mu is equal to minus sigma squared over 2. Otherwise, the expectation is not independent of time. That's only a necessary condition, so you're going to have to finish things off by showing that the expectation of minus sigma squared over 2t plus sigma times WT is a martingale. This is a rather long proof, but the results are going to be crucial to the Black-Scholes formula. Next, I am going to show that with mu equals minus sigma squared over 2, this martingale that you just established is uniformly integral. That's the condition for martingale convergence. We didn't prove it, but we're going to use it. That means that x sub t, which really is the share price as a function of time, is going to converge to some limit x sub infinity. X sub t is a martingale. You will have proved that, so its expectation is independent of time, and therefore the expectation is the same as the value at t equals 0. When t equals 0, this random variable w is normally distributed with 0 mean and 0 variance. That is, it's the constant random variable 0. So x sub 0 is the exponential of the sum of two terms, both of which are 0. X sub 0 is 1. That means the expectation of x sub t is 1 for all times t, and the expectation of the limit is also equal to 1. We know that if we have a random variable whose expectation is 1, we can use it to define a new probability measure. All we have to do is to define the probability measure, which Deneen denotes P sub gamma, that assigns to event A the expectation of the random variable x infinity, where we do the expectation only over the subset of the sample space that corresponds to event A. This is kind of like asking the question, what's the probability that you leave the casino with 3 chips rather than with 0 chips? What's the advantage of this? Well, we can have another random variable on the same sample space. This could be, for example, the random variable that equals 1 if the share price is in between 15 and 20 at some specific time t. And earlier we showed that we can calculate the expectation of that y times the random variable x sub t, alternatively by using the new probability measure and not worrying about x sub t. Alternatively, and frankly I prefer this approach, we're not going to introduce a new probability measure. We can say that if we want the expectation of x sub t times a new random variable y, we can compute that by using x sub infinity instead of x sub t. X sub infinity is likely to be a much easier random variable to deal with because in our example it almost surely takes on only one of 2 possible values. This analysis is nothing specific to continuous martingales. It's true for any convergent martingale, and you'll get to play with some examples where we apply this to discrete martingales. Okay, that concludes my introduction, and we can have quite a bit of fun in class by applying these rather arcane principles to some straightforward casino examples.